Thank you very much for the invitation. It's always a pleasure to be here with you, even if we're distant apart. And I cannot share my screen.
Yes, you should be able to do it now.
Now I can. So I guess you all can see it now. Okay. So today I'm going to talk to you about this work on possibilistic conditions on contextuality that also carry on to non-locality. Before I start, for the ones that we already met before, a lot has changed since we last met. Now I'm based at the University of São Paulo, and our group is growing, and I'm really happy to be there. The conditions for work for me there are awesome. So I'm very happy. And this is one of our, I think, our last group meeting before the pandemic. And now this is how our group meetings look like, but we're still trying to work the best we can. And this work that I'm presenting to you it was done by Leonardo Santos. And he should take all the credit for the things that I'm going to present for you today. And he's a master student of our group. And first, just to set up the stage for what I'm going to talk about, let's just define some notation and some things related. So I'm going to talk about contextuality in the way that was defining the shift theoretic approach. So we start with a set of measurements in some physical system. And we have a set of contexts that represent the subsets that can be jointly measured or jointly performed or compatible, whatever. And for an example that I will use during the talk, I will choose this very, very simple example with 3 measurements and 3 contexts. So I can measure A and B jointly, B and C jointly, A and C jointly, but not necessarily the 3 of them jointly. And I will assume during the talk that all my measurements are dichotomic. So they have only 2 possible outcomes. And I'll mention some generalization in the end. And the main objects for me here is what we call a behavior. And it's just a set of probability distributions that give me the possible probability of each of the sets of outcomes for each context. So in our example, we have 3 probability distributions, 1 for each context. So this will be a behavior in this simple example. And there are 2 restrictions that we can impose on this behavior. First is the non-disturbing behavior. And this condition implies that the marginal probabilities for these 2 distributions in different contexts have to coincide in the intersection of these 2 contexts. And the second one is the non-disturbance condition that implies that when I calculate the, in this example, this is an example of what I was talking before, right? In my simple example, this means that if I calculate the marginal for the measurement A using context AB and context AC, I have to get the same result at the end, the same probability distribution for A, and the same thing in the intersection of the other contexts. So here I have a marginal for B and a marginal for C that is the same no matter which context I use to compute this marginal. Okay, so this was the first restriction. The second restriction is non-contextuality, and non-contextuality is it means that there is a global probability distribution that is a distribution on all measurements jointly, whose marginals coincide with the probability distributions given by the behavior for each context. So In our simple example, it means the existence of a joint distribution for A, B, and C in such a way that the marginal for the context AB is recovered when I marginalize over C, and the same thing for the other contexts. Okay, so there is so if a behavior does not satisfy this condition, we say that this behavior is contextual. And the existence of this global probability distribution can be seen with a linear program, or you can see that the behavior is not non-contextual, that it is contextual using inequalities. There are a lot of ways of testing if a behavior satisfies this condition or not. And the one that I want to talk to you today is called logical contextuality. You've heard about it in Sanson's talk a few months ago. And in this approach here, in this way of demonstrating contextuality, we will not use the entire probabilistic data that the behavior gives me. I will use what I call possibilistic information. And I don't want to know the frequencies of the outcomes. I just want to know if that outcome is possible, it happens with probability larger than 0, or if it is not possible, the probability assigned to it is 0. And the logical contextuality occurs when this possibilistic structure of the behavior forbids any non-contextual assignments of values to all measurements, as we're going to see in a moment. So what I call a possibility distribution over some set is just a function that takes this set to the booleans, and such that if we take the exclusive OR of all values of this function, we have 1, in which the inclusive OR means this set of rules here to combine P and Q. Okay, so given a behavior, I will define, using the probability distributions that the behavior give me, a set of possibility distributions, and I'll call this a possibility collapse of this behavior. And this is a set of possibility distributions that is defined in the following way. I will assign value 1 if here there is a mistake. This should be P. This should be P, not pi. If the probability given by the behavior for that outcome is larger than 0, then I assign value 1. And if the probability, this should be a P, is equal to 0, then the possibility distribution gives me value 0. So the information I get here is just that if that outcome is possible or no. So I'm losing information about the frequency in which this outcome occurs. I'm just worried about knowing if that outcome occurs or not. So the properties of non-disturbance and non-contextuality, they carry on to possibility distribution. So if I have a non-disturbing behavior, the possibilistic collapse of this behavior is also non-disturbing, in the sense that the marginal possibility distributions coincide in the intersection. This is very trivial. And if B is non-contextual, the possibility collapse of this behavior is called logically non-contextual, which is equivalent or is defined as the existence of a global possibility distribution whose marginals coincide with the possibility distribution for each context. But a behavior can be contextual, but logically non-contextual. If we remember, when we make the possibilistic collapse, I'm losing information. So it is possible that there is no global probability distribution consistent with the behavior, but there is a global possibility distribution consistent with the behavior. So in our example of that 3 measurements, let's see what all of this means. So we will start with this example. I have this table giving me the probability. So these are the possible outcomes. These are the possible contexts. And this gives me the probability of this outcome for this context. So this is a non-contextual behavior because I have this global probability distribution that is consistent with this probability table here. But if I take the possibilistic collapse of this thing, I'm just looking at the probabilities that are larger than 0 and changing them for 1. So I have this possibilistic table now. And the global possibilistic distribution consistent with this thing, I just take the possibilistic collapse of the global probability distribution that I had before. So if I have a non-contextual behavior, I have non-contextuality in the logical sense as well. So one implies the other. Now, if I have this other example here, so in this example, I will assume that x is not 0 or 1. So it's something between 0 and 1. And for some values of x, this behavior is contextual. So you cannot find a global probability distribution. But if I take the possibilistic collapse of this thing, I just change what is different than 0 for once, then I always have a global possibility distribution that is consistent with this possibilistic table. So I have, in this example, some cases in which I have contextuality. I cannot find a global probability distribution, but I can find a global possibility distribution. Okay, so here another example. I have this data table here, this behavior. Now I take the possibilistic collapse of this thing. And this is an example of a contextual behavior that is also logically contextual. There is no global possibility distribution consistent with this possibilistic table here. So this is easy to prove. And to prove that, we focus on these 3 assignments here, these 3 possibilities here. So these 3 possibilities, they tell us that the probability of A and B being equal to 0 and 1 is 0. The probability of B and C being equal to 0, 0 is 0. And the probability of A and C being equal to 0, 0 is larger than 0. So this outcome occurs with some probability. So now let's see what global possibility assignment to these outcomes would imply. So if this condition here, the condition that A and B, the probability of A and B being 0, 1 is 0, implies that if A is equal to 0, then B has to be equal to 0 as well. B cannot be 1. Now, if this probability being 0 implies that if B is equal to 0, then C must be equal to 1. So if we want this an assignment of values to these 3 measurements in a way that this assignment is non-contextual, this means that if we assign A equal to 0, we must necessarily have C equal to 1. So the probability of A being equal to 0 and C being equal to 0 should be 0. But this is a contradiction with the fact that this probability here is larger than 0. So I cannot have a global possibility distribution because this would contradict the fact that this is larger than 0. Okay, so these simple examples show us that we can have contextuality without logical contextuality. but it also shows us a way of showing when we have logical contextuality. So this kind of contradiction here implies logical contextuality. Okay, so this kind of set of constraints here that I had before is what we will call a Hardy paradox. And we are going to consider this kind of paradox in cycle scenarios. And the reason why we call it Hardy paradox, because the first example appeared in this paper here in '93. And the what an n cycle scenario means, I have n measurements, and I have this set of contexts. So A1 and A2 can be measured jointly, A2 and A3, and you follow a cycle until you join them again, and A1 and AN and A1 are jointly measurable as well. Again, I'm always assuming that they are dichotomic measurements. And what we call a Hardy paradox in this scenario is a set of constraints like this. I have this outcome here for context AI plus 1 larger than 0. And I have all of these other probabilities equal to 0. And here I have to start with B, then I have all these alphas here, possible outcomes for these things, and I end with A. So this is what we call a Hardy paradox in this scenario, and is easy to see that a Hardy paradox is a sufficient condition for logical contextuality. We just do something very similar to what we have done in our example. So the second condition implies that if AI plus 1 is equal to B, then AI plus 2 cannot be equal to alpha 1. It has to be the negation of alpha 1. The third condition implies that if this measurement is the negation of alpha 1, then this measurement here necessarily has to be the negation of alpha 2. Now, the fourth condition implies that if this measurement is equal to the negation of alpha 2, then automatically this measurement has to be equal to the negation of alpha 3. And then you continue using all of those conditions. And at the end, the last condition that we have implies that if this measurement is the negation of this outcome, then A1 is the negation of A. So if we take all of these implications together, if we imagine that we have an assignment that is non-contextual, this implies that if this measurement is equal to B, automatically this measurement has to be the negation of A. But this is in contradiction with the first condition that tells us that this probability is larger than 0. So this implies impossibility of non-contextual possibility assignment. Okay, so this was known before, and the main result of our work is to show that this condition is also necessary for logical contextuality. So if you have logical contextuality, then you have to have some Hardy paradox in your behavior. So I'm not going to bother with you with all of the details because they are a bit technical. And I just want to tell you the idea. So the idea of the proof goes more or less as follows. If no Hardy paradox occurs, we can derive a set of linear constraints that must be satisfied by the possibilistic collapse of the behavior. So then we study all possible solutions for this set of linear constraints. And in each solution, we show explicitly a global possibilistic distribution that is consistent with this behavior. So it's basically by looking at all possible cases and constructing the global possibilistic distribution for every case. So for that reason, it's a bit technical because we have to investigate all these cases, but the idea is more or less like this. If you have any questions about it, you can ask me later or send me an email or anything like this. Or talk to Leo as well, it would be nice. Okay, so a second result that we have is using this first result is to show the connection between logical contextuality and Hardy paradoxes in simple scenarios. By simple scenarios here, I mean scenarios that have all measurements are dichotomic and all contexts have at most 2 measurements. So in these simple scenarios, it is possible to show that if this scenario is not free of cycles, we already know that having a cycle in the graph of compatibility of the measurements is a necessary condition for contextuality. So if your scenario is not free of cycles, the occurrence of a Hardy paradox in one of its cycles is necessary and sufficient condition for logical contextuality. So what we do here is the idea is, of course, if we have a Hardy paradox in one of its cycles, we have logical contextuality. It's the same proof that I showed you before. But the idea is that if no Hardy paradox occurs, then again, is a bit technical. I will not go into the details here. But we prove that the behavior is logically non-contextual, providing an explicit construction of a global possibilistic distribution, investigating the possible graphs that we have. So we kind of glue the cycles that we have. So we separate the cases in which you have only one cycle. This is the previous result. Then having 2 cycles that connect in a certain way. And then you separate in different cases for the compatibility structure, and you kind of glue this possibilistic distribution and show that in any case you can have a global possibilistic distribution that is consistent with the behavior that you had before. Okay, so another thing that we show is that this connects with previous result. I will show you in a moment, but show that you have quantum contextuality, like logical quantum contextuality in all of these simple scenarios. And the result is that it is always possible to construct a Hardy-like proof of quantum contextuality for simple scenarios that are not free of cycles. So this having a cycle is always a necessary condition here. So for n odd, we use this, the proof was already available in this paper here. So the simplest proof uses a Q-thread system, and you can use any pure state. You will have to choose the measurements according to the state, but any state would work. And for an even, you use a generalization of the original Hardy proof that uses a 2-qubit system and works with any pure state that is neither a product state nor a maximally entangled state. So in our paper, you can see like we have an explicit parameterization of the measurements that you have to use and the state that would work. And we also have, I'm not going into the details here, but we have some other results relating Hardy paradoxes and logical contextuality in scenarios where you have more than 2 outcomes for each measurement. So we consider also other sets of outcomes, still only considering 2 measurements per context. And the results we have generalize the results that were previously obtained in this paper here by Shane and Tobias. Okay, so this is the results that we have so far, but there are still a few things to investigate. And the first one is what we call Hardy-Tisserelson problem, because here we know that it is possible to construct a quantum behavior in which this is larger than 0, while all of these conditions are equal to 0, which gives you the Hardy paradox and the proof of logical quantum contextuality. But we would like to know the maximum of this thing here. So we have the maximum for for the pentagon, five cycle scenarios, and there is some results regarding that problem in this paper here, but we have reached conflicting results, and we are still not sure where the problem is. And it seems that we're trying to do it. Leo is struggled with this a lot, trying to simulate these things using Mathematica and trying to find the largest probability here. And we found a larger probability than what was shown here for n equals 7. So, but we're not completely sure of what is going on. So this is something that we have to investigate here. And other things that we would like to do is to consider scenarios where you have more than two measurements in each context. So this is something that would be nice to investigate logical contextuality in this kind of scenario. And this is what I wanted to tell you today. And I thank you again for your attention and for the invitation to be here.